In this 3D point cloud course, we are going to see 3D Gaussian splatting and how to use it, working with structured dataset like Octrees, moving on to feature computation that makes sense, how to register point cloud together, how to use fun features for your projects, how to leverage clustering and unsupervised segmentation, but also how to move toward classification and what comes after that, using this classification in external software, where we also have the ability to do measurements, do cross-section, explore with more precision what we have under our fingers. Moving on to automated workflow to also manage massive point cloud like this one, and what are the results of unsupervised segmentation workflow and how you can leverage that for advanced application. Hey friends! Today it's a bit special. I want to bring you onto this 3D point cloud course, and I will cover this 8 topics step by step. It will be a bit of mix between a hands-on session where I will show you the various stages and also giving you the fundamentals. You will see that this is also based onto a stream, so a live event. So you will also get interaction and question about 3D machine learning or to set up a labeling data sets and this kind of thing. So it will be very, very rich. So I will advise to take your time. I try to condense everything, so it will not take you more than 2 hours to make sure that you can replicate everything and everything is given. I want to issue a small and fair warning that the sound quality is not as good as before because I had some issues and also with the recording, but hopefully this does not hinder your experience and you get a lot of value of this video that is packed with a lot of tricks, tips, and super condensed. So leave just down below any comment about what you would like me to work on or what you would like me to better explain. And in the meantime, have a great time. These are the various processes that we will touch on today. So only the acquisition side, we will not target that. That was done yesterday. But essentially, you can see that now we have more and more ways to inject automation and AI into the capture of the data to have more autonomous capture. So you can see in all the images that essentially robots are acting as a platform on which you have sensors, which could be LiDAR sensors, which could be cameras, that will allow you to map the environment more or less in an autonomous manner. This is today not the case. Mostly we go on site and do the acquisition ourselves, but know that there is a lot in this domain. And for example, what we've heard from Mohammed working on SLAM in robotics, this is one case where you use the SLAM to guide the trajectory of the robot in order for him to move in space. So this is something that is an active research track. Another one is everything linked with pre-processing. This is usually overlooked, but this is the base of any pipeline, and it is especially important. This is especially important for establishing something that is robust and that will stand the test of heterogeneity. In this case, it's very easy to see that it will be interesting to filter out this point cloud to remove any of the white points that are noise. In this case, if we want to only get the structure of the building. Then after that, we have the registration part. So Eric touched on that, JP as well, with fusing data with different sensor. The first stage is, of course, taking one sensor and having different perspective and putting that in a unified system. So this is what we see here with the arch. This is something where you have also a lot of research track. You can leverage classical methods. I will touch on some of them because they work really well in some cases. In other, they may fail. And when they fail, we push that to more advanced methods that usually rely on deep learning strategies. This is maybe one of my favorite areas, segmentation. I delineate that really clearly with classification. When I talk about segmentation, here it's really having no semantic connotation at all. It's just mostly linked with clustering. So having a data set and identifying groups of points or groups of entities that share a similarity criterion. So in that case, this is a fully unsupervised result in a library that was reconstructed with multi-view image. So photogrammetry essentially, and you can see that you have a major cluster that I found together. This is mostly a planar-based segmentation. And then what is interesting is that you can use directly this as an input to inference classifier, which instead of using every point as input, you can use one segment as input. So of course you reduce a lot the size of your data set, But it means that if your segmentation fails, your classification will fail. So this is also something that is worth investigating. Then we'll touch, and I will show you a way to do that. I will have to do it from scratch because I actually changed my hard drive, which was full, and I forgot to duplicate everything linked to that. So I will remake everything from scratch. How to generate data structure, right? And in this case, a modified nested Octree, and how you can use so-called Potree, and you have various versions for that, in your day-to-day activities to just bypass any limitation with the size of your dataset so that you can explore them quickly. And finally, we have the application layer. So we pinned down some application. I will try to remind me of them so that when I show the various stages, we can touch on that. This is one application that I really like because it shows the power and how crazy it is that surveyors will reconstruct, will take the point cloud and make it as a layer and redraw everything on it when you can automate that. So this is one example where we have a lot to do. Okay, so all of these thoughts, of course, were injected a lot in some papers I wrote early on around the concept of smart point cloud. So essentially trying to see what was done at the time. So we had the point cloud and we had the expert behind the desk, right? That was extracting a product, a deliverable that could be a floor plan, a mesh for simulation, for a VR project, or anything else. But he was doing that mostly manually or semi-automatically. And the idea was to integrate and structure this knowledge in the point cloud itself so that you can use information extraction based on reasoning. So at the time, I was touching on agents that could handle that and structuring the knowledge in a form that is called an ontology so that the computer could use that directly. Today, you can mimic the same theoretical foundations with natural language processing, and hopefully I can touch on that a bit at the end. So pre-processing, this is what we will touch on right now. This is a good example, and this is what I was talking about when I touch on Gaussian splatting. This is the point cloud you get from Gaussian splatting. And when you filter out, this is something that is a bit cleaner, still very hard, I think, to use. But this is a good example of what we should try to do. So just as a reminder, yesterday we used Gaussian splatting to reconstruct splat. And I will just show you what we had. If you remember, with the splat engine, this looked pretty nice, right? Whenever you are close to where I was walking. So to be close to where I was walking, I need to see where the camera were, okay, in the other direction. And you can see that it's pretty nice, right? You have the rocks. Looks like something you could use whenever you see the visuals. Now let's investigate the point cloud. So I have CloudCompare. You can export, and that's what I did, file export splat model as a PLY. Now I will just load that in CloudCompare. And this is what we also did yesterday. Essentially, Gaussian splatting, that's just point cloud with a lot of features, which holds the spherical harmonics, which allows to be leveraged by the rendering engine so that you have a very smooth and nice visualization experience. For geometry only, it's just that if I go and add a new feature, you can see all the features that you have. The feature, for reminder, it's XYZ, there's our geometric feature, NX, NY, NZ, that's the normals, RGB, that's radiometric features, and then you can extract more features, and I will talk about that in a matter of minutes. So all that I want to do is just put some color, and for that I put DC0, DC1, DC2. The normals, I don't think they're really useful, so I will not want to have them. And okay, so this is loading my Gaussian splatting. So let's work with the point cloud from the Gaussian splatting for the noise removal, because it's a great subject as it's super noisy. As you can see, here we have something extremely noisy with splats floating super far away. So for noise removal, the first strategy is, of course, go manual. So I take my point cloud, I take the scissors, and I will just take some points in the middle and I drop all the other ones. This is what more or less I'm left with, and I will zoom in what I have here, and I will do the same once more. I'm really dropping the point outside. If you are doing any processes, usually you keep them, but for this case, I will drop it. It will be maybe a bit better. So this is my point cloud, which is super noisy. If I put let's say the size of my points bigger, you can see we have a lot of floaters that will be nice to try and remove. Various strategies happen to work here, we could, for example, so we investigate here, we see that the floaters mainly are isolated, so they have a large distance to the neighbors. This is something that we could use. We could also use features like omnivariance to check on the surfaces if we have too much variation. We drop the one that are too far away from the local average or the standard deviation. So usually we play on statistical pointers, like standard deviation, to filter that. So one of them is the statistical outlier filter. You have exactly the same in Python that you can do. Essentially, for each point, you will take a number of neighbors. So in that case, if you want to be robust, let's say 10, and you want to filter out any point that is above the average distance within this 10 plus the standard deviation, right? So you have you fit a local model, and then you apply this standard deviation multiplier. If you want to be less aggressive, this will be the case. You are less aggressive. If you want to be very aggressive, this will be the case. But in here, you will filter out all the points. So let's be like medium, less aggressive, 10 point and standard deviation of 5, not to filter out too much noise points, hopefully. He constructs an Octree that he used to filter out the points. Thereafter, we have the result here. So already at this stage, this was the original. This is the filtered one, right? Now we have a lot of floaters, and this may be something that is interesting, where we could use a voxel-based or a spatial-based filtering technique. And for that, we may need to move on to like some kind of preparation, because our point cloud is not to scale and it's not rightly oriented. So I go on the top view and I will just rotate my point cloud quickly. This is just to have something that I can work with. And I will go there and compute an Octree. And you will see that now, if I draw my Octree, this is what I have. And I can select it and go deeper. Yes, until I have a specific numbers that allows me to have discontinuities, which will allow me to filter out really the discontinuous floating elements. So I could even go up until the 8th, which in this case would maybe work. Okay, so let me do that. I take my point cloud and I do a filtering based on connected component level 8, and I want to keep only segments, so clusters with more than 1,000 points. Okay, and this means that now I'm left with there's 4 clusters. There's 3, I think I can remove them for now and work only with that. So this is the result of my point cloud after filtering. Is it good enough or not? Hard to say at this stage. We still have some noise, but it's better than the original. So now maybe we could use a feature technique to go beyond only what we did. And for that, you can go on to edit tools, sorry, sandbox, no others, compute geometric features. So again, this is something that we do in Python. This is just for the sake of a presentation to make sure everyone gets what we are doing and visualize that. Essentially, we will use a local neighborhood radius. So this is based on a fast marching tree. So if I reset that, it does not change at this stage. You can move that to any number that you think makes sense. This is highly impacting what your feature will represent. A very tiny local neighborhood will mean that you really look at a super tiny local region, whereas if you take a large neighborhood, essentially you have more global feature. And you have some kind of multi-scales approach where you compute a feature at multiple scale in order to then do some kind of difference to really understand if you have a change that happened only locally or globally. And that's another type of features that is derived on previous features. And what you can see here is that most of these features are based on eigenvalues and eigenvectors, so principal component analysis, so derivative of the local areas. What is interesting at this stage is maybe for me to show eigenentropy, planarity, linearity, surface variation, and omnivariance. I will let him compute that, because in some cases it can take quite a lot of time, and this is why it's always important to do some kind of pre-processing stages to make sure that you remove unwanted artifacts. This is here the results of our feature extraction, and you can see that we have, okay, so I will open that a bit more. Activity surface variation. So if I take omnivariance, this is what I get. we have all the points in gray are outside the range that is here visible, so they are already filtered out. This is already super aggressive, as you can see, but it will leave only points that looks relevant on the geometric side, but it may be really aggressive if I were to use that. Now we have eigenentropy. Eigenentropy, this is what you have. It's a bit less aggressive, so this may be better in this case. This is mostly the point at the edges of elements that get filtered out. You have planarity, so of course nothing is really planar here. If I were to check what is planar, you can go on parameter and not show that. This is what you get. Again, my radius choice may be not the best here. It's maybe a bit too tiny. The linearity, same thing. Let's check that. So it's still better. And surface variation is really aggressive. So if I do that, we have a lot of points going away, right? And omnivariance, how was that? This is not entirely bad. So let me work with that. So what I do is actually, I will take my point cloud, I will activate a specific scalar field that I want to use to filter out. So it's a thresholding. We are actually segmenting the point cloud based on one feature. So it's thresholding. I'm doing that manually, but imagine that if you code, essentially you compute your feature, and after that, you establish a threshold that makes sense. Here, I use my the visual qualitative analysis to define the threshold, but in case you want to have something data-driven, you can extract that from the data itself. So you will sample something in a specific planar region, in a specific spherical region, extract what kind of feature number you have, and use that to guide the threshold mechanism. And here, I just do that with the GUI. So it will be edit, scalar field, filter by value. And in here, because it's outside the range, I would just export everything that is within the range. And this is what I get. Now, the RGB is really not the best in that case, but it's still viable in some aspects. Just that the black points are maybe hindering a bit the process. But yeah, I think that will be fine for the next stages. What I can do is reapply a filter to remove all the noisy points. So let me do that. This time I will take only 5 or 6 neighbors, and I will be really aggressive. And normally I should get something cleaner. So let's see. Yeah, this is a bit cleaner, and I will delete the floating point again. Okay. And this is good, and the rest I drop it. So we have one main element, which is much cleaner than the one at the beginning, yeah, which was rotated and had a lot of stuff. So this is our new point cloud. Again, this is extreme, what I did, because the Gaussian splatting is extremely noisy, but this will allow us to monitor a bit better what we are dealing with. One last thing that I can do maybe is I will duplicate my point cloud, not to make any mistake. And I want to show you a little trick to improve the qualitative visualization aspect. In this case, I mentioned this is from, this is not true RGB. These colors are normally superimposed with the Gaussian splat spherical harmonics. This is why this looks really saturated and we have blacks and stuff, but normally this is how it should look like whenever you use the spherical harmonics. This is something I did not do, but you can do that, of course. Now, if I wanted to improve that a bit without doing a heavy process, you can use the PCV, which is essentially doing some kind of occlusion test and creating a scalar field that you can then superimpose on your colors. So let's try that with a 1024 resolution so that it doesn't take too long. It's sending rays from above. Oh, it's so good that I actually duplicate it, because I think when I did the rotation, I put it upside down. So everything may not be as I want that to be. Yeah, this is what I meant. So it sends the ray from above in all the spherical direction to create a scalar field to mimic a bit where you have something black and something which is not black. The problem is because my point cloud is upside down, this is how it happens to result in. So I will delete that, take again my point cloud, and just do a rotation around the x-axis. This is fine. To put it in the other direction, I will clone it again and do my occlusion. only Northern Hemisphere, plus and press OK. And this should bring something which is a bit better in our case. Just checking if there is anything in the chat. Okay, so I need to order the point cloud in takes a few hours. Okay, so I may do that, and we may have that for the second part on 3D machine learning. Nice. So this is what we get, and look, it really, I like this kind of visualization, especially for such natural point cloud. But you can see also very clearly how noisy the geometry is with the Gaussian splatting. When you look there, it looks all smooth and nice. But if you take a measurements, the underlying, and here it's filtered out, is really not as smooth. But again, this is also full of grass, so this is also why. You still can use that for doing counts and various measures that don't need specific metric accuracy, but more exhaustivity accuracy. So if I were to count the rock mass here, maybe that would be enough. And this is something that we can use thereafter. So what I will do here, now that I have that, is try to combine colors, enhance with intensities, and normally it will use my scala field to enhance the colors. Let's check that. We are between 0 and 1, so this is good. And the intensity field is illuminance, PCV, and I press OK. Yeah, so this is not entirely bad, but because of the saturation of my colors, we see weird elements, blue and red on the rocks, but it's still better than just the colors themselves. This is something that we could filter out after. We could increase this as well. So if I were to enhance that one more time, maybe that will make that a bit better. Let's check. No, does not change. Okay, so we'll leave it like this at this stage and visualize that afterwards. So what I do is I take my point cloud like this, file, save, and I will save that as a last file. And for that, let's go on to the bootcamp chapter 3, and you will have the data set then filtered point cloud. And I will keep the LAS for now. 1.2 custom scale. Okay, we leave it like this. Use minimum bounding box center. Okay, and do I want extra field? For now, not. I will just keep the parameter as they are. Okay, so now back to our process chain. This is the filtering that we did, except we already did some kind of formatting for the registration part. So let's maybe explain a bit on the registration side what we want. Here in the case that you have not aligned point cloud, you want to bring them and align them. So I could do that. Do I have some point clouds? Imagine you want to bring these two point cloud into the same frame of reference. They are the same, but we could like play with them, put on some Gaussian noise, add some specific, remove some points and such. In this case, it will be interesting because we can monitor if it's like perfectly fitting. The same registration, you can do that also within Python just to show you what's happening. So there is two stages here. There is the global registration challenge, and there is the local registration problem. The first stage is to try to push that and bring that in this frame of reference. And the second stage is to try to fine-tune the alignment so that you have as a minimal distance between both shapes as possible. And this is what is done whenever you go onto SLAM mechanism. Each LiDAR pulse will bring your point cloud, and you have a timestamp t where you move with a small displacement, and then you want to merge that with the previous one and so on. So what is done here usually is the global stage. We leverage RANSAC to find point that belongs to mostly the planar surface, and you will also use the bounding box to align center and use RANSAC to bring them all on top of one another. And also you may use also a bit of a rotation around that to find a global registration automatically. And the second stage is then to use a local registration mechanism like ICP, Iterative Closest Point, to try to really bring the point clouds together much more tightly. So let me showcase another way with points that will be the same in both point clouds, so the local and the global. So this is the local one. Let me check in both cases. So this is the good one. So tools, edit color, I will put that in blue. And this is the one that we want to change. So you can select both of them And normally you have a way to like push them together, which is here, aligning two clouds by picking at least 4 equivalent pair of points. Try to take these points in areas that are easy to pick for you. And here, essentially, you have a least square mechanism that will give you, the more points you have, the better the fit will be. So let me align quickly. Select the to be aligned entities. So select all, global and local. Okay. Okay, no, sorry. I just take them again and I align. What is to be aligned? This is the global to-do registration target. Okay. So this is the to be aligned and this is the reference. So we are good. Now what I do is I will go, for example, I will take 5 points. So one here, one at the entrance. So I will go there. I will take maybe the first one will be at the entrance. The second one here in the corner. The third one will be down in the tree. So we have 3 there. Okay, we have a pole here, interesting. So I will put one on the pole, A3, and one here. Okay, A4. You have to do exactly the same thing on the other point cloud. So the first one was the entrance. Where did I took it? Oh, sorry. First one was around here, I think. I'm getting very rough. The second one was there. The third one was on the tree. The fourth one was on the pole. And the final one was here. Or no, it was done. So you can remove the final one. No, was here. And what you can see is already the error. So let me add the person. So you can see the error for each of the points. So 1, 2, 0, 0. The problem is, no, in this case, we are to scale. So we have 1 meter difference, 2 to 2. So we have a problem in the pointing of the R0 and R1. So let me check where they were. Yes, and here. Yeah, okay, there they are a bit. Okay, so this one, this is normal. So the R1 is not good. So I will delete it as well. And you see that the fit is much better because we had an error in my point. So let's keep this fit and put a line and validate. And you can see we have the transformation matrix that we could use. And we have the final root mean square error, which is around 20 centimeters. So this is a high, but normally if you are below a certain threshold, you can be fine for the next stage of iterative alignment. So I guess here it will be fine. So let me press OK. And this is what we have after this first stage. So we have a problem with the ground, but yeah, this is our global registration. This is what you can expect to have whenever you do that automatically. The second stage is to do the same, but instead of picking pairs, we will finally register point cloud with ICP. So the to be aligned is the global and the reference is the local. You can define a number of iterations, else you have a stop criterion that is based by the root mean square error, right? So this, we will keep that. In some cases where you have like various perspectives with a change in scale, you can add that. Of course, this had another parameter to estimate by the algorithm, so it will be less accurate or it will take longer. And we can use normals also to guide in order to fix the rotation around the z-axis. Here in the research tab, you can give how many points maximum you want to use. So that's a sampling limit. This is for the algorithm to be efficient. If you just care about exhaustivity and accuracy, you should move that up a lot, but it will take much longer. And you can also ask what kind of rotation and translation you want to adjust. In this case, I want to keep it and leave him the choice to change each parameter, so rotation, translation, but not scale. So 6 parameters. And you can also ask him to enable any point that is too far away by clicking here. So let's just keep it this way. I think it's fine. And at the end, you see that it aligns. Yeah, okay, let's check what's happening. But he says essentially we have an RMS that is worse. So I think we did something that is not good. Theoretical overlap 100. Ah, no, okay. It's okay, so it's because it's a perfect match. This is why CloudCompare cannot handle well the visualization. That's interesting. I've never seen that before. Okay, so this is a perfect case. This never happens, but here it's because we have exactly the same points. Still, it allows to check what you can get from this mechanism of global to local registration. Now, registration, we did that. Let's move on to segmentation. And this is where I think it's important to speak about features and also various ways that we can do segmentation. So with CloudCompare, I cannot show you all the way to segments, but I will speak also about others that are super interesting, and maybe I can go through that before going on to the CloudCompare side of things. So there's some example of segmentation that can be useful for you. Above, you see that what we do is what is called difference of normals. So I spoke about the nature of features and how you can play with scale when you compute them. What is happening above is exactly what I did. So you have this street scale level point cloud, and I computed normals. So to compute normals, you do a principal component analysis, and then you take the eigenvalue with the eigenvectors with the lowest eigenvalue. And this is the third component that will point up of a local surface area. So essentially, what that means is that you have a point, you take a radius around it, or you take a k nearest neighbors, you compute your eigenvalues and eigenvector, and you get your normal. Then you change the radius to something bigger, and you compute your normals. And then you do a difference between the big one, the small one, and you divide that by the value of your deviation in both cases, and you get the difference of normal, which is a measure that will hint at where you have a change in the normal direction based on the radius that you have. That will highlight a lot the edges much better than taking a single normal, and also it will be much more distinctive and robust to any like local global change. So this is what is done. And then after we do a magnitude threshold, and you can see what you get. And from that, you can do Euclidean distance clustering. And this, in this case, you will get some windows, the side of the buildings and things like this. So this is one way to leverage that. And maybe I can show you how you can do that in CloudCompare. This is feasible. Another example is whenever you have tightly bounded point cloud like this one, you have the capacity to still use features to extract special characteristics, compute facets, and do the k-mean based facet refinement and then region growing. So this is also a process that I like because it shows you that you don't go directly to the optimal case. You need to go through an intermediate step of having segments that are a bit bigger than points and that are used then through a region growing mechanism. I will speak about that a bit later. This is another example where you get the results that you see here by going on to, again, a segmentation that will compute some kind of groups that are really not making a lot of sense for taking them as an individual component. But then you use that with growing mechanism to obtain what you have on the left. So this is called supervoxel, superpixel, or superpoint mechanism. So creating this kind of groups of elements on a local subset that will help you drive advanced segmentation mechanism. This is another example for indoor data by Stanford. And in here, essentially, this is the labeling process that is illustrated here before moving on to pushing a canonical space that is then used to train PointNet initially. So you can see that segmentation does not necessarily apply only to geometry, but you can also have that to spaces. And this is very important to understand that sometimes what you are searching for is not a geometry component, but more a space-aware connective segmentation or segregation. Two concepts to have in mind are over and under segmentation. So over segmentation is when you create too many segments, and it's actually a burden on the computational capacities because you will not be able to go on to the result that you initially wanted. And the second stage is under segmentation. And this one is super problematic. Essentially, this is when you have a region that bleeds over multiple objects that you want to obtain. So this could be having a segment on an edge that bleeds over two facades. If you want the facade independently, this will be problematic. So this is what should be monitored under segmentation. This is the metric that should really be monitored. On the cluster extraction side, this is very, very powerful. This is what we did with the connected component algorithm, but essentially this does cluster extraction. This is super powerful, but it means that you need discontinuities, Euclidean discontinuities in your point cloud or your feature space. And this is something that is not easily feasible in some cases, especially for land, vegetation, and natural elements. This is something that is not super easy. The region growing algorithm, this one is given to you in the 3D segmenter OS with an advanced version. This one is super useful in a lot of cases on 3D datasets where you can essentially take as seeds, you take some points or some cluster and you will grow a region based on checking a feature. In this case, you grow a region based on the normal. Whenever you have the normal that will change higher than the threshold that you delineated, then you will have a new region that is created. And you can also be smart about the decision at which point you start with for growing a region, like starting in planar region. This is something that is usually smart. And also you can adapt the threshold based on the data and have something that is not fixed for all points, but knowing that if you are in a curvature intensive area, maybe the threshold will be a bit higher. This is something I will speak a bit about later, because you have ways to have this mechanism work without any knowledge injection, so fully unsupervised. Right, so for segmentation, let's keep this one maybe, because it's a good example. We have everything here that is tight together. If we want to segment that into various features, I think we should use features that look at if an element is planar or not. So for that, you know the drill now, other compute geometric features. The radius, I will put it a bit higher in this case. And I want planarity, verticality, linearity, this is okay, and omnivariance to check if we have points that in some certain areas don't follow something which is usually flat, or you have a lot of deviation between points. Okay, so this is the extract from what we have. This is using verticality. So you can see that we could use verticality, for example, to filter out the ground. But before going there, let's check the other features. So omnivariance, I thought that will help for the trees. It does not, so we may need to use something else. We have branches, but that's all. Maybe linearity will be useful for the branches. Yeah. So linearity, you see that you have all the linear feature really nicely taken, and that could be the seed then to grow some kind of clusters for the trees. What else do we have? Surface variation. So this can be useful for the elements that is grassy on the ground, but also to detect whenever you have change in the normal direction. And this is what you have highlighted here. And verticality is good to like define the ground from the rest. So I can start with that. If I were to filter that out, I would do edit, scalar field, filter by value, and I would split, not here. I would take my point like this. The problem is I have floaters here. So I will need after to delineate them. So edit, scalar field, filter by value, split. And I will call that segmentation. Okay, so this is what I can work with for the ground. As you can see, we have all the floaters here that are a bit annoying at this stage, but are easily taken out by just going on the side. You could also use edit scalar field, convert, export coordinate to scalar field, and only the z, for example. And this will allow us to filter out based on the z value. So I will not be super aggressive, but I will take that. Again, I'm doing all of that visually, but you can see if we take the histogram here, just to show you, this is what you have. So this is also very, very handy and powerful. In this case, you can detect the peak, right? And this would be a hint to segment elements around that, fit a Gaussian, and that will be the ground. So you can directly see the Gaussian here. If I were to fit the Gaussian, it will have a slight slide because of here all the various other elements. So what I can do is stop at the value 3.14. We have the 68% of the point, which is linked with the Gaussian, right? The sigma value. So I could take that 3.14 to filter out my point cloud, and this is done like this, filter by value, 3.14 and split. Okay. So I will just seeds. This goes in seeds. So now we have that. This is mostly the ground that can be refined. And this is the remaining elements, which could be further extracted, I guess, with other strategies. But in this case, I think you really need to have a planar-based detection to get all the elements on the facades and all. So here I will go with region growing or planar face detection. Maybe I can do something around it with Python for that just right after, because with CloudCompare I may not be able to show you the extent of what we can do. Just let me try something. We see that we have something that is mostly planar, right? So we can use shape detection and use that as a way to guide our segmentation. So that could be RANSAC. If I go there, you have the possibility to use RANSAC. We will take only the planar elements and have 500 points as a support. Keep all the leftover points in a new point cloud and do the least square fitting on font shape. I don't want to simplify the shape. And for now, I will set a random color, but else you don't do that. Max normal deviation, 25 degrees. Okay. Sampling resolution, the distance between neighboring point in the data, I will put it at 0.5 is okay. And the max distance to the primitive, 0.2, so 20 centimeter. That's high, but again, I don't know the resolution and the precision of this point cloud. So let's try it this way. Okay. And yeah, as you can see, it's not entirely bad, right? We have found most of the facades in our point cloud as segments. And normally he saved the leftover points here. So I just take all of them, toggle, and this is what is left to activate the normals. So this is kept as noise, but again, you can have a refinement step that will take as seed every time your region and grow a bit to make sure that all those remaining elements get taken out. So we could continue in this fashion until we have everything in a segment and then move on to the next stage, which is classification. So classification, what I mean by that, this is a meta category that hosts classification task, semantic segmentation task, instance segmentation task, panoptic segmentation task, object detection task. Essentially, everything falls within this umbrella. This is not the case with 2D. With 2D, a classification task is really, you have one element, which is usually an image, and this image will be tagged with a class, right? Here, classification has all of that under the umbrella, except whenever you deal with object detection. If you pass in an entire point cloud through your algorithm, then you can add a label to the entire point cloud, which is then a label classification task. You also have things called part segmentation, where you have an object and you want to delineate sub-objects. So the chair is one object and you want to go beyond that and have the legs, the backrest, the seats, and things like this. So for the classification, as I mentioned before, we could use that as a guide. So toggle. I will just show you also a way to quickly select the various plane. So select children by type plane, okay. And then I think you can, no, select children by type or name. I will just delete them for now. And all this point cloud, I will bring them in the same one, yes, and remove the normals. This is our main building, and this is the rest, and this is the ground, and this is the remaining elements. So I have to put the ground there, and I have to put the remaining elements. So this is what we have. So we should be normally working with that, but again, what you can do is increase the threshold of the RANSAC maybe to keep that. And I will still work around with trees. So to work around with trees, I can use, in this case, I think a connected component being aggressive, and normally you don't want to drop any point. This is just to have something a bit clearer. You don't want to colorize it. This is again just to showcase what we can obtain. So this is an over-segmentation. Then this could be the base to grow from. in this case, and it's much easier to work with. Like we have the main trees, and you can grow taking this big region and attaching all the other elements based on that. So usually, especially for forestry, terrestrial laser scanner, what you have is a graph cut approach, where after that you construct a graph and you compute the connectivity of components in your graph that is guided by some kind of algorithms to define and delineate these major segments. So this was just to show you what you could obtain. What I will do now, because we are a bit limited with the time, is I will do the same but be less aggressive. So I will keep 8 and 10, and you see that we have major segments obtained. Essentially, I will just check the major segments. Okay, and all the rest. Yeah, I cannot here guide it too much on the size of the segments. This is a bit annoying me. But do I have, for example, this tree here? Yeah, this is a tree. We have the tree pretty nicely taken. Here it's maybe a bit big, but still it's a tree, so that's fine. And all the other remaining elements are dropped. And here we have also windows. As you can see, we have all the windows independently taken, which can be useful. And here we have the entrance as well, taken with a bit of trees. The pole also is taken here alone. So that can be a good base. So the next stage from that will be to just work. Again, you should not do that manually because else it takes quite a lot of time, except if you are constituting a labeled dataset, in which case you have to go through that. So what I will do, if I were to doing that, is I will select my various trees, for example, and put them. Okay, so you first need to have to constitute 2 groups, so leftover and group. So in here, I will take my trees like that and put them here, group that I will call tree. And every time I put them here, I deactivate them. Okay, tree. This is just to see a bit clearer. This is also a tree. All right, all of that is also a tree normally. This is a tree, this is a tree. Now I will create a new group pole that I will put in between. For some reason I cannot, but that's okay. This is a pole, and we had another one, I think. Yeah, there. A bit over segmented. That's also pole, and that's also pole. Haha, I'm okay. Yeah, that will be the stairs. But let me then bring in the group of, show the tree, and show that would be the building, ground, and I would call that noise, even if it's not really noise. This is just to show you the next stage. Now we have the building, the ground, the noise. I put that here. We have all the trees and the poles. So what you do is you take the trees all in and you merge them, and you keep the new original cloud index. This is for the instancing. Same thing for the poles. So I put that here. For the poles, I bring that in, and yes. Of course, here I have a problem of over-segmentation, so the instance is not really the pole, but that's fine for the demonstration. Now, this is our final point cloud. What I will do now is make sure that the building, we have an original cloud index. This is if you want the facades, right? So we have a facade decomposition, which is fine. For the ground, we have only one element. And for the noise, also one element. For the trees, we have multiple elements. So we have original cloud index. I will just go there, Scala field, rename, instances. The building, I will call that then facades. And the original cloud index, you rename that as instances. Ground noise trees, we have instances, and poles, same thing, edit scala field, rename instances. Okay, so the next stage is I will just duplicate all of that, and I'm taking them and merging that, and I generate this scala field. This is why I renamed. Now, normally we should have everything in a single class. So the last stage that I can do is, instead of having that called original cloud index, I rename it and I call it classification. And this is my classified point cloud in trees, building, ground, and poles. So you can see that it's absolutely not perfect, but it's a strong base for already getting something that you could use to classify or to extract specific features. This was done in under 15 minutes manually, but you can automate that, and maybe this is something that I can show. But before showing that, we can move. I just check if there are any questions. No, I think we're good. We can move on to the final stage on this part, which is structuration. And what I will be doing with structuration is creating something. This is what we did. We gathered the point cloud, we studied the characteristic, we generated features, we used them to create labels. This is possible to prepare the data set for the next stage. And now we will create a visual tour for the point cloud analysis. So this will be also our application. This allows me to speak a bit about the standard format, just to make sure that this is clear, because I remember yesterday, I don't think I touched on that. You have three main categories. You have ASCII file format, which is very useful if you want to stand the test of time, because you can open that without external software. Normally, each operating system comes with a way to read ASCII file, which is essentially a list of elements that is not binary. So you have XYZ, TXT, OBJ. These are the kind of ASCII file that you will get. For the binary part, this is something that is much better if you look for optimization and compression. The problem is you are usually linked to having some kind of library or some kind of software that can create and read this kind of elements. So this often happens that you have a software that makes super cool stuff. 5 years down the line, they stop because they are not profitable or something, and you are stuck because you did not convert that into a format widely used. We have hybrid format. PLY is one case where you have a little bit, usually in the header, that is plain ASCII, which allows you to read the file. And then you have a part which is binary that just asks you to have some elements to read that more efficiently. So now, before going on to the command line interface, let us go and install or show you a way to handle massive point cloud. As I mentioned, I deleted that from my hard drive, so I need to do that. So you have a tool which is called Potree, which was developed in Vienna. That's a spin-off of the Scanopy project, and Markus Schütz, which is a bright graphics, computer vision engineer, made a version for the web with WebGL. So that's Markus. And you have various distribution. You have one which is Potree, which is on the web, which needs from you a server. This is not so hard to do, but this is not entirely straightforward. And you have another one, which is called Potree Desktop, which essentially rely on Electron to create a distribution of this web version for the desktop. So it's easy to just get it. You go there, at least for Windows. You download the Potree Desktop. We'll download it. Yes. And I will just install it on my hard drive. So I go into software, I push it here. The thing is, you have nothing normally to install. You extract it to Potree. You are not seeing, sorry. This is what I have, Potree 1.8. I will just rename it. Okay, this is what you have in it. Actually, the exe file is the Potree desktop.bat. So what you can do is create a shortcut, and on the desktop, you can just rename that. Okay. Viewer. And put another icon if you don't like that. This is me being crazy, but I think, Okay, yeah, and the icon, change the icon. Okay, something, yeah, this one, okay. So this is our point cloud viewer. I had it before, but as I mentioned, it's not anymore working. And it opened a Potree instance, which is local, and you don't need any dependencies on the web. So now, what he did is also nice, is that he integrated the conversion, which is called Potree Converter, which allows you to go from any like last file format to the modified nested Octree. And if I were to take what we extracted before, which should be now here, so Bootcamp chapter 3, then the filter point cloud, if you remember, in LAS file format, if I drag and drop it here, you can convert it. I suggest to use the 2.0 because you have less files, okay, but it's not compressed at this stage, and you start the conversion. You should not take too long, so this is done once, and after the file is accessible directly. So now you have your point cloud where you can move around in it directly, which is pretty nice. So, okay, this one turns out not to be as good as what we have on the Gaussian splatting side, but it allows to check for any consistencies that you may have. So you see that it's super noisy, yeah? Super noisy. Nevertheless, we have some interesting elements there. What I can show you maybe is on a bigger data set. So now in there, you have your point cloud that is there, and you can show other information. If you had classification, you could show classification, intensity, and for the classification, maybe this is something that we can try, is exporting our data set with the new classification file, save. This is a tiny one, right? But still, chapter 3, facades.las, save. And all that I have to do is drag and drop in the viewer. And this is what we have now. This is the classification field active. So this is a great way to share things with your collaborator as well, right? Without moving too much out of your comfort zone. You have also a lot of tools like measurements. So this is a measurement that I can take, right? 16 meters. You have possibilities to create section, cuts and sections. So here, this is also interesting. If I were to do that, and now show, I have my cut, we don't see it really, but if I just show only inside method, where is it? Did I created it? Yeah. Normally this should be my profile. You can show the 2D profile, yes, but I want to show only inside. You have your cut that is there, and you can adjust it. So if I take my profile, I can have a larger width to play around with, and you can show the 2D profile, which is super handy in this case. So let me open, because you can have all the characteristic on the left, as you can see, and this is really nice. So you have the trees, and you can extract some kind of element. And in here, you also have the possibility to extract this profile only in LAS file format. So that means that you are not stuck to only working with something in read-only. You can extract element and rework them in CloudCompare. So for example, if I wanted to work around with that, I could do that, extract the profile. And now if I go there, I have my profile, apply. Yes, okay. Yes, I shifted it, but this is the profile then that you have. So you have the in and out. You have a lot of cool stuff to do. One thing that I want to show you is the massive point cloud, of course. So that I have on my data point clouds. What I can show you. Yeah, okay. So for example, this is a huge point cloud. Let me restart to make sure that we have something that you can replicate easily. So I open my viewer, and this is a huge point cloud that is 100 giga, like 120 gigabyte. It's converted. I just drag and drop it, and in less than a second, you have the entire city that you can navigate. And of course, this is where you could move around, extract some specific features, make some kind of analysis at scale. So this is really interesting. You can also load in other point clouds and like combine some kind of elements. So let's go on intensity gradient, monitor the height quickly. So if I were to put elevation, this is then easy because you can actually work with normally the range, right, to color elements. So this is also cool. It's exactly the same filtering capabilities that we saw. And classification, if it has, yeah, you can then show what is the ground and what is not the ground and work around with that. You have also the return numbers, everything linked with your point cloud. So if you did not know you could do that, I think this is a really super interesting tool. Working with classification also allows you to like do some projects pretty efficiently. So in here, we have that in high vegetation for some reason, no vegetation. So you could compute how much area you have taken out by like this little fountain, I guess. Yeah. You just go on to the tools. And here, if I do that very quickly, you see what you have. As a fun fact, this is actually with open data today, especially. This is something that I use almost every day whenever I need to check out if a project is suitable or not for the legislation in France. For example, if you want to create a pool in your garden, you can use point clouds with open data. Like put here, if that was a pool, you know, more or less the size, like a nice pool, 10 meter by 4, right? And you could check if it's on a parcel, you could check if this is in the area fitting to the regulation, if you are allowed or not. You could check out if the construction that you have has a height which is suitable for the local urbanism plan. So there are a lot of things that you can do directly, and leveraging also the classification is something that is very, very powerful, especially, for example, Eric, you mentioned in Norway, the capacity to have a very nice data set. In France, you also have a nice data set, which is already classified. And this allows you to filter out only point on the building to be able to leverage that for getting this like how much building you have on a specific area or things like this. So this is something that I really wanted to show you, and that is really useful. Now, maybe I can talk a bit about how you can bring that all in with Python, and how should I do that is spinning off maybe a mini Conda first, if you remember from yesterday. Conda, I will just open that and zoom in. Conda list. This is all that we have. Yesterday we had the bootcamp, so I can go back onto this on the activate bootcamp. And normally I should be good to go here. We have matplotlib. We have all the libraries installed normally. So that should be good to go. And we used Spider yesterday, so I will just spin it off and we can move around from there. So just looking at the chat, if there is something that I've missed. What about LAS and NAS? Yeah, that's good. LAS and NAS works the same. If you mean the difference between LAS and NAS, LAS is compressed and NAS is not compressed, so they use it's LAS zip, so they use a zip compression on it, whereas the LAS they don't, but both works. The thing is, of course, if you have a compression mechanism, you need to have a decompression mechanism. So opening a LAS is longer than opening a LAS file. So that was what we did yesterday. Let me create a new script to spin off CloudCompare with various processes. So the first thing that I want to do is maybe save as chapter 2. I will call that pipeline or automation point clouds.py. Save. Set console working directory in here. So this is not tested on Windows 11 and macOS. So this is just that. And I can import 3 libraries for now. So subprocesses, this is what I mean. This will allow us to work with changing specific software. So one, importing libraries. And as I mentioned yesterday, I like to work with the cells because it allows me to move step by step. So the first thing that we will do then is also maybe import matplotlib, and we will give way to operation, one operation at least, or operations that we will call later on. So that will be our variable of operation that we want to do. Okay, so essentially we will call a subprocess, and this is how it goes. So let me just copy what I had made before and modify it. So we just use subprocess, and we will call a subprocess, which in this case is CloudCompare. You see that I have to pass my path. So if I open here, this is where CloudCompare is installed, cloudcompare.exe. Okay, so O is for opening. Maybe I can show you that with CloudCompare. If you want to use the subprocesses, you need command line access. So CloudCompare has this compare. It's called CLI. And we talked yesterday about reality capture, the same. It has CLI, so you can use that. And with Mushroom also. So you can do that for the acquisition part as well. So O is for opening, basically in the command line. This is where you have all the available options. So this is for the latest version. For mine, maybe it's a bit different, but it should not be too different. And what you can do is just chain various commands. You have some example, I guess, at the end. Yes. So if you do CloudCompare open global shift auto mileage coordinates, this will open and switch and do spatial subsampling and export your data. So you have some kind of example, cloud-to-cloud distance, cycling over files. You have also some bash to do, bundler, mesh conversion. So these are the small example here. We could chain the various processes that we had. So the first thing is we should open a sample. So in my case, I should have a sample data, but we will take the one from the chapter 3, which was chapter 3. So the facade is already processed, but maybe the one that we loaded will be nice, right? So that was this one, and I will put that into a data folder. And I will call that sample, but that's a PLY, so let me transform that into ASCII for now. Oh, but no, CloudCompare can open PLY without problem, so we don't even have to do that. So you can also use that for EO operations. It reopens CloudCompare, which is fine. Just let me bring all of that in here and close that. Okay, so we have in data sample.ply. So this means that I can do that, export format LAS, save cloud file, and we'll do results. Okay. Right click, copy as path. It should be something, yeah. And I will just do that. The problem is I have a little space, so I will remove that if I can. Yes. Okay, so let me try that. I think we have an issue because of that. And this I comment for now. So let me import that. Execute. And just check quickly if everything is working. DPCD sample does not exist. Yeah, this is my mistake because it's here. Okay, and I just need to do that. So now if I do, why does he have a heart? Did I put a heart somewhere? So I guess so. I heard someone needs to join. Okay. Okay. OpenG, this may be problematic to work on with a space. This may be the problem, so I may need to move that out. Just let me try by switching to slash instead of backslashes. two file name, but they are one cloud. So the backslash is fixed my problem. The last thing that I need to do is make sure that I open one file. So call, open G. So essentially, just to show you, this is a list that I passed. This is how my list look like. We have the path to my program. We have open, and every time with the subprocess, it will just in between add a space. This is fine. My drive, course bootcamp, chapter 3, data sample. I just need to check if that's the right path. Chapter 3, data sample.ply. So this is good. Export format LAS, save clouds, file. But because I have only one file, this is maybe why it's not happy. I may be able to actually bypass that. So let me take that, push that here, comment, and yeah, just set to last, change cloud output format finish, and that's the save clouds that is not happy. Two file name, but there are one cloud. So I just need to make sure that I use save cloud the right way, which is here all at once. Okay, file.xxx. So I will just put save clouds without my little, this is if I add more. Not entirely sure here. Let's check. Check my draft, chapter results. Okay, I understand why now. File, I forgot to put results.lis. Still not. Save clouds. Okay, check console. Drive, bootcamp, chapter 3, results.las. So it did save it, but where? Save cloud finished. I think he is not happy with me giving the path. So if I were to do that, I guess it will work. Problem is maybe he saved it in the wrong folder. So let me call it. Yeah, save clouds. So if I go to data, okay, it's saved in the original directory, which is fine in LAS. So things are working through Python. Now, what we can do is just define the base information for simplicity and then move around from that. So let's do that. We give the path, we give the data path, in our case then this. We can give the output path, so in our case it will be this. Results. The name, export, and file opening is a PLY. And I think from there we can do some kind of EO operation. So this is how you would write something. So for the import part, you see that you can create a variable, you pass in the path. You don't want to bring in the timestamp that we had at the end. You want to save it and you open the file path. And for the export format, the file output and save clouds. So file O is PLY. Nah, that's why we can put bin to have something in the format of CloudCompare. So now maybe we could try that or add algorithm in between, but if we were to change that, let's do also some kind of linkage. I know I'm not entirely clear. This is absolutely live, but things will get clearer now. So import, export, that the two steps. As I mentioned, I create one variable per step, and algorithm is also a step. This is spatial random Octree subsampling, and CSS subsample is the operation. So now, the operations that we want to do, are the following, so I can just delete that for now. Okay, and this should work. So let me just make execution. We define the path, we define the variable import export, and we make automatic subsampling, and we chain import subsample export. So let's execute that. This works. So now normally in our result folder, there is nothing. So maybe it's in our data folder. Yeah, it's in our data folder. If I take the subsample and I bring it in CloudCompare, we see that we have our subsample point cloud here. So things are working. So exactly this way, you can also link another stage, which could be automatic feature extraction, right? So for that, you can add that, where you give the type of features that you want to have. We said that omnivariance is interesting, planarity, linearity was useful, surface variation not so much, verticality was useful, and that's pretty much it. For the radius, 20 centimeters is maybe a bit low, so let's put it to 30, and eigenvalue we can keep them. And for the featuring, you see that we will have feature and the type of the feature that we want. So you could actually use or leave all that we had before, but just compute feature, and you have to pass in the type of feature that you want. And then down the line, we just put in the features that we want to use. So again, we have CC import, CC featuring 1, CC featuring 2, CC export. And featuring 1 will be 0, 1, 2, 3 verticality. Sorry. Verticality, and the CC feature 2 will be planarity. Okay. So now if I do that and that, it saved my clouds. And if I go there, we have our featuring here. Yeah. You can see that we have our various feature computed. So this was planarity, and we had verticality. We have a lot of outliers because I think I did not define properly my radius. For the registration, same thing, you can do that. And essentially, this is just a matter of checking what kind of function that you can use, like CSF filtering is also super useful. This is something I did not show, but I can show here. If I take my point cloud, you have the CSF filter that allows you to fit from below a cloth based on the mesh, and depending on the resolution that you give, it will allow you to delineate your point cloud into ground and on ground. So here I will make a resolution of 1, and I will put a tiny threshold and export the mesh. And as you can see, you have now the mesh fitting is there, and the ground and non-ground point are there. So these are the ground point, and these are the non-ground point. So in this case, it would be much better to use that instead of the thresholding that we did before. And you can chain link that the same way, and you have specific elements to export the ground, export of ground, and so on. So this is super useful. What I wanted to share here is really that you can actually leverage CloudCompare as if it was a library through Python. So considering CloudCompare as a library through the command line. And any of the software where you have APIs, CLI possibilities is something that you can do. So that allows to get out of only using a Python library directly, but also working with other stuff. So I do that very a lot actually with Unity. Blender, there are two software that are really nice, especially for creating scenes and renderings and combining stuff. You have possibility to code as well. So you have also the integration of Python within. So this is super useful. And in other software, more for BIM, you also have some possibilities with Revit and other software where you can do the same kind of stuff. All right, so let me check where we are standing. So this is something that we did entirely with the converter, getting the nested Octree. So I think already here we covered a lot on the processing chain from pre-processing to classification and application. we covered a lot of stuff. So I propose to stop there and reactivate a bit your microphone and camera so that we can have a bit of a brainstorming, maybe to share some ideas about how we could move around stuff, or if you want me to deepen a bit a certain aspect that I covered right now. So let me go in the option and allow mic and camera. Okay, so yeah, if you want to take the floor, please don't hesitate. So Mohammed, I think you have your mic on. I don't. Okay, so I will disable the mic. I think he. Okay. Does anyone have something to share or some solution that he think is useful for others?
I think there is a wonderful question in the chat box. Just recently, someone asked about registration.
Sorry, yeah. How do you choose particular point from registration when automating process? This is a fantastic question. You can try to use the feature extraction process to find invariant points that you can match automatically. A bit like extracting SIFT features for images, you can do that with point cloud. But usually you move into a process that will work. Okay, so let me show you, it will be better. What you can do in the case of automating such a process is two-case scenario. If you have ground control points, you can leverage that automatically and match that with another data set to bring that together. So this is what we do with laser scanning and targets. This is how we bring things together. Now, if you want to really not rely on any artificial targets that you put on site and only work with data, you have to work with the geometry. So where are the registration, global and local? That's not this one. Okay, let me work with that. So the airline. So let me check except yeah, the airline. Okay, so in here, what you can do is the following. So you have your point clouds, and I will do something like this, right? To showcase how this is possible. Usually, you will be able to extract with RANSAC a plane that you will constrain around the z-axis. This is usually how you do. And here 500. I'm not sure that it will work this way. Okay, so you have the plane, and here you will have the exact same plane. Okay, you can really say, I want to extract a plane somewhere below, or you could use the CSF before, and you will use that to match both surfaces together. So your point cloud will already be well matching with the other one. Then you can guide that even more because of the facades in this case to match to get the correct rotation. Of course, you have a bit different point cloud, but this is essentially the idea. What I mean by that is that if you cannot pick point, you cannot automate that really directly with feature extraction because the features that you extract are not really distinctive, then the best solution is to work with the geometry. And this is one example of how to work with the geometry with shape extraction mechanism. RANSAC is one way, but you have also OOG that allows you to extract some kind of shapes, and you are not necessarily working only with planar feature. You could extract spheres. So also on site, if you want to detect that, you place some spheres and you detect spheres with a specific radius and you use that to match. The matching part is essentially a graph matching problem with least squares. So you construct graph in Euclidean space and you match that. And this is straightforward to do. So that's how you solve this global registration problem. If you don't have any rotation issues, if it just translation or things like this, you can also usually go very quickly with a bounding box matching. For example, you take the bounding box, you match them, to the same position, and that will sort out this problem. Hope that makes sense. If you have any question or input on the various stages.
Yes, please. Is it possible to segment according to an external data, for instance, true north, a specific angle?
True north, a specific angle. So if I take then the data sets, what would you like to do? So if
for
that's
instance, you extracted all the facades, all the walls, but it would be interesting to get all the walls facing north, all the walls facing south, or all the walls with specific angles, some kind of stuff.
Yeah, so this is feasible in Python, but here I can show you that each plane that you have. So if here I extract I will redo it. So I do the CSF, okay, and I take only the off-ground points. And here I do the RANSAC part with 500, and I will be max distance to primitive 35 for now. And here you have the ability to then leverage for each point cloud, you have a plane that is generated based on the RANSAC shape, essentially. And you can see that you have a direction, right? So you have a normal vector and you have a direction. So you can, you can use that to know if it's north or south or something else. The same happened to work in Python. So maybe I can show you how to do that. But you have that through the courses as well. So this is how RANSAC works, right? You have iteration, takes 3 points, you fit a plane until you reach the scores that is good enough for the algorithm to stop. This is an example that works, but is useless. So usually you use that planar based for specific cases. What I can show is cases where you use that to detect that. Okay, it's not here. I will add that as part of the resources, the way to do that with Python. But that means for you will need to have this extra step of like doing the collinearity check between the vector of your true north, so the dot product of your true north and your facade. And with that, you are able to discard any facade that is not oriented to the north or to the south or to the east or the west.
Excuse me, I have just one more question.
Yeah.
So we were talking about the automation process, and I wanted to ask, like there were some data that I think yesterday you were showing us about the street, and it was like so nicely labeled. Even the road markings were very nicely classified, and the homes were very nicely classified. Cars were. So is there any way to get that level of automation? To get that quality classification, or that quality classification always needs some person to do it?
A very good question. It depends at which stage you are in the process, essentially. This is more linked with the second part, so the last chapter of this bootcamp, which is touching on 3D machine learning. And the goal is to have, if you go in this direction, you don't use algorithm per se. Well, it's an algorithm, but it's more, you really need to make sure that the data that you provide on which the model is trained is of very good quality. So that means that if you take the process from scratch, you will need to go through a labeling phase where yourself you will have to label at least a part of the data set and then use that to train your model. So hopefully that answers your question, but essentially this is just a matter of having a super nice data set and having a model that is able to pick up features from the data set to be distinguishable enough for different classes that you want to detect. These are some examples of what you can expect. So this is with the Segmenter OS solution, the region growing one. This is the unsupervised like result that you should get with planar-based segmentation, and then you can use each segment through a machine learning 3D machine learning model to be able to classify that if it's the ground, if it's the how do you call that, the pylon, if it's the rebar, if it's the ceiling and things like this. What can I show? So this is an example of what you have with open data, and this is also something with an automatic classifier, right? But that was trained on data with these various classes, which is very interesting to get at scale or have color information that you can leverage. This is not always the case, but this is what we showed yesterday. This is what you are able to recreate with what we had yesterday. This is not Gaussian splatting, right? It's the point cloud, but it's dense enough so that you can have a lot of information on the various aspects. This is another example, maybe, of unsupervised system, right? And what you see here, this platform, this is one of the things I was talking about yesterday when I say creating assets and apps. This is something that I initiated in 2014 for the land surveyors in France, and that is still really relevant to make sure all the data is centralized, but essentially the tech stack behind is not very far from what we are seeing today. It's just the way of managing everything which is handled in an engineering way with modules and blocks that you can have tied in together. This is one thing also, we'll speak about that a bit later. This is a self-supervised system where we use ontologies to know that cars are parked in a line, and this is fully automatic. So this is with Jean-Jacques that we did that in 2020. What else can I show? Yeah, I think that's pretty much it as far as point cloud and such goes. Is there anything else that you wanted to touch on before making a little pause, maybe?
Yeah. Do you hear me? Yeah, I just wanted to know how long and how many time does it take to get some train algorithm, or how many files you need to with normal segmentation just to start working on more messy file.
Yeah, great question. So if I take back, this is fully unsupervised, so you don't need to train anything. So it's just the time that we ingest is in conceiving the algorithm and fine-tuning the algorithm. Through the segmentor OS, you have that, and the implementation is there. So it's just a matter of understanding what you do and using it after, but you don't get directly the classes, and you need to work from there. So you have a labeling phase, but you don't work at the point level, you work at the segment level. Now, the second stage is creating your model that can classify in various classes. Do I have one somewhere like here, for example? It means that, so not in this case, but in normal case and what we will see just after, we need to label a data set. So you can use CloudCompare or anything else, the process that we did, to try to be as quick as possible to generate a data set. Usually, it's a good rule of thumb to have 1,000 objects per class for good quality detection. The trick is that if you work at the point level, you have a lot of points for one class, so that you can diminish that. The other thing is you need to make sure that you have a balance between the classes. So here it's not bad because you have a lot of cars, you have a lot of trees, you have a lot of building and the ground, but you don't have a lot of poles. So this is likely to be poorly detected. So essentially, to build a model, you can expect like at least the first hand model, and then you can refine iteratively. But you can expect, if you have the data, if the data is organized well, you can expect to spend between 1 week and a month on the labeling effort to constitute your data set. This is not necessarily fun work. You have some tools that allows you to accelerate that, but you have still to go on to the quality check, because if it's not good quality, you will not have a good model. Once that is done, this is what we will see just after. Building the model is not very hard, and this is a bit the novelty with this new data-driven approach, is that the focus is not into the expert knowledge around the algorithm, but the expert knowledge around the data to be able to make something really nice, and hopefully have an algorithm that you pick on a shelf, more or less, that will work good for your case. So this afternoon, we will see several classical machine learning ones. You can expect to have very decent result with that. At any point, if I will speak about the threshold, when to switch to a new algorithm or when to continue labeling, this kind of things. This is really dependent on the score that you will have. But usually it's good to have in mind that if after the first passes, your data set is labeled, your model is established, if you have something that is above 80% in global accuracy over all classes, then usually you are in a good standing to have something that you can push in production with the current model. If you are below that, sometimes we need to investigate other models, deep learning ones, to make sure that this is something that we can achieve. Hope this answers your question.
Yes, perfect.
Okay, awesome. Afef, you wanted to say something?
Hey, hello, yes. So I have just a question. So let's say, for example, we don't have labeled data for the 3D data, but instead we do have labeled data in the 2D space. Is there a way to go from the 2D to 3D? Do you think like we can just segment the 2D images and then do construction? But I'm not sure if.
I lost a bit the end. I got the beginning.
Hi.
Yeah, I can hear you.
Cool. So I'm just asking about if we do not have labeled data in the 3D space,
yeah,
but instead you have the labeled data in 2D space. Should we segment the 2D and then do the reconstruction, or is there kind of a trick to go between these two?
Yeah, you have tricks. Very, very good question. So do you have the link directly between the 3D and the 2D?
What do you mean by link?
Do you have the position of the 2D image based on the 3D?
Yes.
Yeah, indeed. It's just a matter of making sure that you have the position of your image based on your point cloud. And what I really recommend then is essentially if you have the labels in the image space, you are in a projection, let's say, setup where the challenge is having a projection that is as sharp as possible, right? So this is actually super cool stuff, and this relates to a field that I like, which is called semantic photogrammetry, where you actually label images and you classify your point cloud based on your images and the pose estimation. The only thing is, the trick is, in that case, because you have a multi-view setup, you need to make sure to fuse prediction for a same pixel, right? You need to fuse prediction. If you have not a setup with multi-view, so if it's a single view, usually you will want to go into a orthographic projection and have some kind of raycasting mechanism to check the depth so that you don't label points that are behind something. If this makes sense, you've heard of the segment anything model?
Yes.
Yeah, okay. So this is something that I can also share. So this is also part of some course, but I have a tutorial there. It should be the tutorial section. Let me share the friend link to that, because in it you have the projection equations that I already wrote. So okay, so this is one example. You have an image. This is the result of SAM. The only thing is which projection you use. That's what I'm saying. If you have only one image, just the orthographic one is the one that you should use. And you will project. So you have to use the masks, maybe not directly the pixel color values, but masks underlying. So attach to each pixel your mask of the class and use that you transform your point cloud. But this is essentially some ways to do that, and you have all in the. Okay, so that's the spherical projection, and the mapping. The mapping, I put it somewhere around. So you get here I do that with the color, but you will have to do that with the masks to get the mapping. And this is what is done. For example, that was the 3D point cloud put in a spherical projection. On top, we can use SAM here to detect the various components. And then the last stage is to back project that to the point level. So this is what is here. And you get that. But you have to filter out the points that are not seen from a specific point of view. And if you want to label the entire scene, it means that you need to generate different point of views. The data sourcing that you know how to do, preparing and filtering also, and how to handle large data set, we have something. So now the idea is to try to build a predictive model with AI, and that's what we are going to do just next. Beautiful. So now that we have completed these 8 stages, the next logical step is to dive onto 3D machine learning. So this is something that I will also share in this specific channel at any point. This is already ready and available for people at the Academy. If you want to head straight on there, just please do so. I'm always super welcoming to new members there. But if you are happy to wait, then maybe in the coming weeks, coming month, you will also see that happening. Have a fantastic day and see you in the next video. Bye-bye.